Hello everyone. Can you hear me clearly? Good, good. So today we are going to go a little bit more into hands-on about MapReduce, and then we will also discuss the problems which we had uh, talked about in the last session. All right. So here we go. So before going further, so today let's talk about something called streaming job. So we talked about general philosophy of what is MapReduce and how do you generally form keys and values. But how do you exactly execute any program? So the easiest one out of all is streaming job. A streaming job essentially makes it possible to use any binary as mapper or reducer. Like for this example, the way you run a streaming job is using this kind of command. Okay. So this first line is the Hadoop binary. Then the jar is the command which we give to Hadoop binary. Hadoop client, basically this is that Hadoop client, which is we you also use it for HDFS operations. And then this is the library which contains all the logic about Hadoop streaming. This is the library provided by Hadoop guys. Now this is most important thing. So this command is essentially your mapper. This command is essentially your mapper. And this is your reducer. Okay. Now, what does this command do? This command does very simple thing. Whatever input given to this command, this is a Unix command which basically replaces space with new line. That's all. Just like you say control F and then put something and replace it with something, or you can say control R. So in the editor, the way you replace a text, similarly this command replaces one text with another. In this case, we are trying to replace space with a new line. Okay, we are still talking about our usual word count example. So our mapper basically will i- make the input file such that there is only one word per line. All right. Now this command basically takes the input, whatever input it is given, and counts the number of unique values in the input. Okay. So unique minus C command basically counts the number of values in the input, provided the input is sorted as in ordered. So basically what is it doing actually? Imagine that this is your input text. All right. Now in this input text, what is it doing is first it will replace the space with new line. It becomes like this. And imagine that this is being splitted by into multiple reduces, like in this case. and then after it is sorted, it comes to this. Okay, let me give you an example of a single one where, okay, so all right, so this is the very simple example. What is it being done by a streaming job is essentially your output of the mapper is being sorted by the streaming job, and then giving it to unique. All right, so streaming job makes it possible to use any binary at all, to use that binary as a mapper or as a reducer. So here what we have done is we have taken any input file, replace spaces with a new line, and then we'll have one word per line. In this case we have these one word per line, and after that this output is being given, this output is being given to uh, this output is being sorted by MapReduce. And after it is sorted, your unique minus C command is being executed. Your reducer is being executed. And all reducer does is, if the input is ordered, if the input is sorted, then it counts how many unique words are there. Okay. So this is what you'll get. So you'll get the word count using these two commands. Right. Similarly, this another diagram, the next diagram shows that how does it make it multiple reducers, okay, using the same map reducers. Now, so does it make sense to you, or I am out of context completely? Does it make sense to you? Okay. So Ram's question is, what does that jar file do? Okay. So okay. So, so jar file is essentially Java's MapReduce code. Okay. When we'll talk about Java MapReduce, you will understand what does what is inside the jar. Jar essentially is a collection of Java code. Okay. So you just like DLL in Windows, just like DLL in Windows, we have jar for Java program, and we basically pack all our stuff into a single file and give it to Hadoop. And in this jar we also mention, automatically it gets generated that this is my entry point. So Hadoop jar will basically execute the jar, find out what function is going to take care of map and what function is going to take care of reduce. And this jar essentially understands what are its arguments, and then based on those arguments it executes those map it It delegates the work of its reducer to those commands which are being passed to the command line. So here we are passing these command lines, as you can see, and these command lines is what is being executed by this jar. Okay, so Hadoop delegates its work to MapReduce here, and this delegated its work to mappers and reducers. Okay, how to specify the number of mappers? So the way you define reducers is clear, as in you can define by specifying -d equals something. Similarly, I think we can define maps like this, okay, as an argument, as a command line argument. All right, so like this. Let me have a look. So we'll have streaming job, number of maps. So what does it mean by generally executing? Let me see if generally you don't define the number of map reduces. Okay, okay. So I'll have a look at what is the how do you specify mappers, but as a thumb rule you don't really define number of mappers. Okay, okay, you don't define number of mappers generally because number of mappers is decided by how many files or how many blocks are there on how many servers. Okay, so if a file is distributed on 10 servers, automatically there will be 10 number of mappers. All right, if you try to define more number of mappers, I need to understand that what behavior is going to be, because that means that data is going to be read from one place to another. Okay, all right, so probably Hadoop doesn't provide you the arguments upfront to define number of mappers. All right, now going ahead, what is the difference between streaming and pipes? Okay, streaming looks like a pretty simple case of, I mean, it sounds like cat minus file, then sort, then your mapper code. Okay, mapper code SED for example, and then, sorry, something of this sort. Alright, this is your my mapper code. Right, we'll talk about it in a bit, but as a quick example, so basically what piping is doing is basically taking the data from one place to another, and and here it's whatever input file you have given. If you had to do same thing using command line, this is how you will do: cat minus file my files, then your mapper code, and then sort, and then reducer code. Probably that's what Vishnu meant. Now, so the biggest difference is that streaming job essentially is for the data which is lying in your HDFS. Second, Streaming job is for the situations when you have multiple computers and you want to get your work done using multiple computers. All right. And none of these jobs, streaming jobs or usual map reduce, make sense if you have a single computer. All right. So this is what MapReduce looks like. And what you can do further is we'll do it later. Basically, if you have got lot of commands, if you got lot of commands, you can put it in another file and ship it together. Okay, I'll show you this. So let's talk about a little bit about hands-on. How do you do it? And let me just take this command. All right, so we are going to do. All right, I'm putting it one in a single line. All right, so output folder need to be different. Sorry, let me just increase the font. All right, so what we are trying to do is we are specifying input folder here like this. Input folder, what does it contain? As you can see that, let me just go to our Hue. There you can see the files. So it says asgiri slash word count slash input, asgiri slash word count slash input. Okay, so whatever, there is only single file. Had there been 10 files, they could have been all concatenated together and given as input to your mapper. Okay, and the output is going to be saved here. And the mapper command is very simple. Sed is basically a command from Unix which replaces one string with another. Although it has far more features, but for example sake, all here all it is doing is replacing one thing with another. And in our case, we are trying to replace space with new line. All right. Now, and here all we are trying to do is this. Okay. So it has done the job and saved the work here. So let's just go back. Where did it save the work? Asgiri output 30 November. Asgiri output 30 November. So as you can see that it has generated the counts. It has generated the counts, right? How many times a word comes in. Now, as you can notice that the double quote, single quote, they have not been removed. Okay. Exclamation mark. Like for example, if you can see this in our input, when it was doing word count, there are so many kinds of right? You would definitely like to clean it up. When you are doing word count, okay, so we like to clean it up so that we get a proper work. For that, what we are going to do next is we are going to clean it up using this. So it's a chain of commands. We are putting it together into one file. All right. So we have just taken it and put it into one file. All right. Now in mapper, this time we are specifying this, okay, our file instead of the usual command. Now we have created our own command. We are going to use that one, and we are also going to mention something called file, so that while doing the execution, the work gets distributed, and as well as this file gets shipped to the node where the work is getting done. Okay. So now our SCD command, instead of using the my.sh, we are going to use my.sh instead of SCD. So it says output folder exists. Let's just create another one. Let's call it clean. Basically, what I'm trying to do is read all the content from the input folder, then pass that input content via my mapper while my mapper generates one word per line, and then it essentially, for each of the output of the mappers, it is going to sort it. Hadoop is going to sort your output of the mapper and then feed it to your reducer, where reducer is essentially going to handle the input. The one thing you will notice differently in case of streaming job, the reducer doesn't get the grouped input as in key and array of values. That's not what reducer get in case of a streaming job. Here it only gets the keys sorted by the whole set of keys sorted together. All right. Now you can see the output has been generated, and this time it is most likely going to be far cleaner. Where is ASCII? And here you can see that, right? So this time it's far cleaner, and so as you can see that each word is fairly clean. All right. And so right now it is not sorted by counts. If you again feed it to another chain of map reducers which have nothing in them, says echo both the places, then you will get these numbers already. Will get the output sorted by the key, which is numbers this time. Okay. So and there you can see the output. Now for time being, let's say Hadoop cat, and my file is ASCII output 30 November clean. So I'm trying to print this file, and I'm using the local command called a sort, and we'll put more. Sorry. Here we go. So whatever output I get from this, we need to change it to -n. And so it's the word the which is the most popular, then of, then and, then to, then in, and so on. And in this you can see that looks like protagonist is Pierre. Okay, looks like this guy is the protagonist because rest of the world, okay, rest of the words are essentially English dictionary, standard one. Okay, so based on simple word count itself, you can figure out a lot of behavior. I mean, lot of things about the input text. Okay, so those words concatenated with the numbers is essentially this is how they must have been in the input file. Okay, this is how they must have been in the input file. All right, now, all right. So makes sense to you? Is this the work of a streaming job clear to you guys? So yeah, Anna, is this clear that these are the actual words that are existing in those files? Maybe some typing mistake or something. All right, and yeah. So is the streaming job clear to you all of you? Okay, next question. All right, for right if you need right now, I'll just paste it in the window. Rest it will be available in the presentation. All right. Are the numbers removed in the output file? Okay. All right. So if you had to do it, do the same thing what we had done is basically can we if you look at it, what we have done is instead of piping and using sort command, we have used Hadoop. Okay. If your data is small, you should be very happy with the sort command itself instead of doing. So, right, there will be an example of using Java into MapReduce. Okay. All right. So those who do not understand piping, should I give a little bit more detail about what does it mean by piping? What does it mean by this command? You see here. So here for cleaning up the word, what we have done is For cleaning up the word, what we have done is we have put a chain of commands together. Okay, so let me just show you this. So echo hi and you. Okay, all right. So I will do one step at a time. Hi you. Okay, now so first of all, what does it mean by this line? This line essentially means hi, comma you. Okay, so echo anything, it just prints it onto the screen. Okay, so echo is a command. These are the arguments. All right. Now, now we want to replace the space with a new line. Okay. So we want to replace the space with the new line. So we do pipe. Pipe means take the output of this previous command, which is echo, and give it as input to this new command which we are typing. So sed is a command which replaces one word with another in the input to it. And what is input to sed right now? The output given by echo. All right, here we go. Right? So you can see that instead of having hi you in the single line, it has broken it into two. Now the next step is we want to replace anything which is not alphanumeric with nothing. Okay? Basically, again we are using sed command. What it does is it says it uses regular expressions in which it says replace anything which is not A to Z, capital A to Z, and 0 to 9. Replace it with nothing. You can see two slashes, there is nothing in between those second two slashes. And so this, replace it with this. So basically, there are three slashes. First first two slash, anything between two, first two slashes is replaced by anything with the between the two slashes, second two slashes. Okay. Now you can see the comma has been removed by this sed command, as you can see that. Now the next command which Unix provides you is tr. These are standard commands. Okay, tr says that translate anything which is capital into smaller, and here you go. All right, so effectively we have chained these commands in together to generate our desired output. And this chaining of commands, piping, and Unix command exist since 1980s. All right, these are not something related to MapReduce. All I am trying to demonstrate, your usual Unix commands can be used as streaming job very happily. Right now, so Ajit's question is the streaming job is something that helps you sell command as mapper and reducer? Perfectly, you are right, and you are completely right. That's what it is. So not only shell script, but any command. Okay, any command which you can execute in from Unix shell can be used as any program which can be executed on that computer can be used in mapper and reducer. I assume that I'll get the same performance even if we use other. Yes, you will get a same performance. Okay. Although whenever you are executing an external program, there is a minor delay, but that delay is generally insignificant when we are talking about distributed computing or we are talking about batch processing. What is the significance of the word streaming? Does it imply? No. So that is a little bit of misnomer. It has nothing to do with video streaming or any other thing. What it does is, as you can see, we said used SED. Interestingly, interestingly, SED means streaming editing. Okay, or effectively, whenever we have certain input, passing it to another, and then the whole chain of things, we generally call it streaming. All right, and basically, we will stream the data through one stage to another. That's what it generally this kind of streaming means. So whenever we pass the data around through the pipes, we call it stream processing mostly. All right, so that is how we call it stream. Is it possible to automate the shell script? Yes, definitely it is possible to automate this shell script. So whatever we have written over here, you don't have to execute these things always from the command prompt. You could use a tool like Uzi where you can schedule it and pass the output to another processes. Okay, all of that is possible using Uzi kind of a workflow. All right, now we have got, yes, this is using Yarn right now, but you don't have to worry about Yarn because Yarn is effectively an architectural change. It does have the map reduces, it has everything same. Now, so this was a quick streaming job example. So, do you have any other questions? I hope I've answered everyone's question. Did I miss any question? All right. So, I guess everybody got it. So we basically did in a simple way that whatever commands we use generally on our computer, we use those commands as mapper and reducer. All right. Great, great. So now the next question, I'm going to go for a little bit of problem discussion which we had last time. So first set of problems which we had was, do we require the frequencies computation? Do we require MapReduce for frequencies computation? And how do you do the computation of frequencies? Yep. So if you have got humongous amount of data where reading writing is a big challenge, reading writing the data is a big challenge. The amount of data goes into terabytes. In those cases, it makes sense to to distribute the work of reading the data onto multiple machine, and therefore it can be quite helpful if you run it on multiple machines. Now, frequencies of letter essentially would give you at the end of the whole process 26 numbers, right? 26 numbers, that's all. We are ignoring all numerics, all special characters. We are just interested in counting. We are just interested in counting the frequencies of letters, right? So at the end of it, if you look at it, we don't have to we don't have to take into account, we don't need too much of memory. If you have to do it without MR approach, all you need to do is create an array of 26 integers. Okay, we just have to essentially keep 26 numbers, or if we had 26 fingers we could have just counted. I mean, although on each finger we have to keep marking how many times one letter has come up. So we scan the text character by character and keep counting which character has come in out of these 26 one. All right. So the problem with associated with this is RAM is not a limitation, but the network or disk IO will become the bottleneck, and CPU will become the bottleneck, right? Now, in the MR approach, the mapper does essentially the same thing. For each of the line given to the mapper, all it prints out the 26 numbers. Okay, whatever it does here, it does the same thing here also. The same mapper is there. It takes the input line, because to a mapper each line will be given as input. Now mapper has to do something about it. So what mapper does here is that it it takes the input line and prints out the frequency of various letters in that line. All right. So imagine that there are two mappers. So mapper 1 might be printing this A this many times, B this many times, C this many times, and D this many times. And mapper 2 might be printing like this. And reducer basically sums it up. Okay. Reducer basically sums it up. So the input to the reducer is going to be A 234 comma 12, and if there are more mappers, those numbers will going to be there, and then reducer just have to sum it up. All right. Right. So Vishnu's point is that can't we use the same logic that we used for second session's word count, replacing word with the letter? Right. That can be done. That can be done. All right. That can be done. But to split a word into one letter per line is not a straightforward process. It's not a straightforward process. You'll have to break the whole array and make such that each character is per line. All right. Now moving on. So is counting the frequencies okay? So even if you do not do this, if you even if you do not count like this, if you do not create an array, it's okay. All you need to do as a mapper, all you need to do is for each of the letters, you just for a whole line, all you need to do is print one character in each line. That's all. Or print out for each line, print out, say you have got 30 characters in the input line, print out the give the output in the std out key as the character and value as 1, and that's all. So exact the same approach for each word. It's just that this time we are talking about characters. And to further optimize this whole process, we'll talk about in after some time how can you make it further faster, because on each mapper they're going to be they're going to be uh, on each of the node running the mapper, there are going to be multiple A's, right? Because each line might contain different number of A's and so on. To, can we do something on the mapper node itself further before it is sent to the reducer? We'll talk about that process also after some time. Okay. So is this okay? So let me just move to the second question. So finding anagrams in a huge text. Who got this one? So so did you think about this question? Okay. So what will be the key in your mapper when you the in the output of your mapper? What will be the key? Okay. So key for the word cat, tag, and act has to be same so that when the reducer runs, reducer gets all of these things together. So what could that be? Okay, okay, interesting. Harish says sorted word as the key. Do you mean to say that a word sorted by its characters? Excellent. Any other approach? Ajit says that. And why do you need to reverse the cat for the value P Malik? Okay. So let's say what we are trying to do is we because we have to find anagrams in a huge text, right? So if you have got this kind of anagrams, there could be first approach that take the first word, take the first word, right? And okay, or let me say take a word, then generate all rearrangements and find those. Oh, okay, so that will not work. Let me think about some other alternative approach. So how do you generally do such kind of problem in usual programming? Is basically take one word, compare it with another one, then another one. then another one, then another, and so on. You keep on doing it again and again, right? So take one word and just check if they are the rearrangement of each other or not, then compare with this one, and so on. But this approach is not efficient. Okay. A good idea could have been that we just print out the sorted, we, we take the and generate sorted characters. Okay, sorted characters, which means EHT, right? And sorted characters as a key and the value as the word itself. All right. So we generated this for cat. For cat, what will be the sorted character list? Anybody? Act. Perfect. And let's, the value is going to be cat. So even if we had a hash table on which we are putting these keys, we can quickly identify that for the, what is the sorted characters, right? This one, right? Now for act, what will be the sorted characters, right? Act only. And the, okay. Now in case of in, it is going to be in. Now for tick it is going to be ICT. Good. Okay. And for tag it is going to be, okay. Here we are rearranging the characters of each word in ascending order. Anna, is that clear now? And we are putting the value of the actual word as is. This is the word, and after rearrangement, this is the word generated, right? Then we have to is becoming what? EOT, right? Now, all right. Oh, sorry. You are right, Anna. I was making a mistake. So tick is basically CIT, not ICT, because C comes first and then, yeah, I couldn't notice that. Thank you, Manish. Good, good. All right. So did I make any other mistake? So for each of the word which is coming as input to your mapper, what you have done is you have generated the sorted word itself and the value as the actual word. Okay. Now now what will mapper do? Mapper will take this input, whatever. Is this font good enough? Okay. Mapper will take this input and do a sort. Okay. So in my editor, I have this provision of running sort. So it will do the sort. As you can see quickly, all these three words, act, cat, and tag, have come together, right? As soon as you sorted. So which means that for each key which has identical each of the values which is identical keys, they have come together. Okay, and and therefore these are the acronym of each other. These are the anagrams of each other. All right. So you don't have to do anything in the reducer. Okay, you don't have to do anything in the reducer. All you have to do is, as part of reducer, you just have to print out the comma separated values. That's all. All right. Sounds good. So seems like any solution to this problem will not work with MapReduce, right? So mm, Manish, a little bit more details would be good for me to understand. Could you describe it a bit more? Had it been something like scan the text, find somewhere, find in rest of the text, that kind of approach would not work in case of MapReduce. You need to break down the problem into the key formation and utilize the sorting in order to. Yes, so that kind of approach where I was comparing one word with the rest doesn't solve the problem, right? Because that is not something which we can parallelize so easily. You'll have to think about some other technique to parallelize that kind of approach, right? So everybody comfortable with this? Ajit, Harish, Kesi Reddy, Manish, P Malik, Ram, Ruman, Sanjay, Shilpa. Good. Anna, Vinay, Vishnu. Yes, yes, go ahead, P Malik. So P Malik's question is key has to be unique. Okay. If the key is not unique, it's okay. If keys are replicated, those values will come together. Okay. If key is not unique, then the values will come together. All right. As part of MapReduce process, the values will come together if the key is not unique. All right. So everybody on the same page? Good. Good. Let's move ahead. Now, right. Now next problem. Now this is the another visualization, same problem. Whatever visualization we have done, given this amount of text, our mapper generated these key values. These key values were sorted. This line, that straight line that comes here, is being done by Hadoop. Now, and they were grouped together, and reducer basically took them and printed this. Okay. So Harish's question is, if the value is text, it will be concatenated, and if it is number, then it will be summed. Very good question. So he has this doubt that if the values are text, okay, then they will be concatenated, and the numbers it will be summed. So anybody wants to answer this? Okay. So that's exactly why we have something called a reducer. Okay. So reducer is effectively given an array of values. Okay. Reducer might be given an array of values containing many kind of data type. Depending on what values you have poured as part of your mapper process. Okay. And therefore, reducers will be given your reducer. Reducer is your code, remember? So it is the duty of the reducer, your reducer function, to basically concatenate or sum or maybe average, do whatever with the array of values which reducer would be getting. Okay. So reducer might get this, okay, and it might generate something like A and concatenate it with concatenate it with something like 190 plus divided by zero point 0.3, and maybe it generate later on, how should I put it? Okay, let me just put this way. Okay, so you get 190.03. All right, let's imagine this. So it will be up to this will be up to your reducer what it does with those array of values for a particular key. Perfect, perfect, great, great. So you guys got it. So reducer is that sort of thing. All right. And also note that one thing you should note that in case of a streaming job, the input reducer gets is the whole content sorted by the key, not grouped one. So you will have to group it by yourself. Okay. And grouping a sorted set of keys is straightforward. Okay. Now anagram is done. Okay. Now this one, quick. A file contains DNA sequences of people. So we have a file containing user ID and DNA sequence. Okay. Now all you need to do is find out all the people with the same DNA sequence. What will be your approach? We want to find out all the people who have got identical DNA. Okay. Which means we'll have to bring together all the people whose DNA is identical. P. Malik, think again. Okay, Vishnu says that key equals to DNA and value equals to user. Good, good. And so all we need to do is for each DNA in the input. So imagine that your mapper is getting one line at a time, which means only these two things at a time, and you need to figure out what becomes the key and what becomes the value. All right, all right, good enough. Okay. So map gives DNA sequence and person ID. Good, good, good. So P Malik, are you okay with this? So basically, instead of right. So basically, we need to. Why do we need to put key as the DNA? Because we want to bring all the users whose DNA is identical. Okay. And as we talked about, in case you specify, in case, I mean, as we talked about, MapReduce brings all the values together whose keys are identical. All right. And therefore, we design our keys such that solves our problem. Okay. So here the question is extremely simple. All we need to do is define our key as DNA and value as user, and that's all. We are happy. Anybody has doubts about it? Because next question is the a little complicated version of this one. All right. So we are essentially exploiting the ability of MapReduce to sort any amount of data. Okay. And it tells you that, hey, give me your data and tell me on what basis should I sort it on, and I will sort it on. Okay. And give me a reduce function. I'll execute my sorted data on I will run your function, reduce function, on the on each of the keys in my output. That's what MapReduce says to you. Any other questions? Okay. Mapper happens in the node where data resides, but does reduce happen in the same node, or it will most likely happen on a different node? Okay. Yes, there will be a network load. So the general tendency is to keep reducer on one of the nodes on which mappers is being run, so that the network transfer is minimized. All right. So is everybody clear? Should we go ahead with the next question? Manish, you got your answer, or should I describe more? Good. All right. Now this one is a little twisted version of the previous one. Here, what we are saying, you need to bring together the users whose DNA is either identical or exact mirror image. Okay. So what will you do? What will be your keys such that all such users whose DNA is identical or DNA is exact mirror image, they should come together. What should you form the key? Or what key will be same for these users? Okay, okay. So Vishnu, as we talked earlier, you cannot compare one key against other keys. Okay, great, great. Ruben says that the key is DNA and its mirror image is that is ACGT in alphabetic order. So ACGT comes first. Good, good. One is that. And okay, Hari says we can compare start and end of DNA. All right, all right. So let me think about what approach you're trying. So you can compare. Okay. So what will happen in case. Okay, let me think about Harish's approach. Harish is saying that I think I got what Harish is trying to say. So ACGT, okay, and in case, okay, what you're saying is that in case A is less than T, the first letter is A and last letter is T. So we will get ACGT in this case because A is smaller than T. Okay, that will be your key. And in case we have something like GCTA, in those cases the key will be ATCG. Is that what you're saying, Harish? Good, good. What happens in the case of ACTA? I'm discussing that. Okay. All right. All right. So you are on the right track. You're on the right track. Just you need to be able to express this in a more simplified manner. So all we are trying to do is comparing the inverse of itself with itself, right? And whosoever is smaller, that's what we are printing. That's right, Harish? Because first you check the first letter with the second letter. Now you want to compare this with this. And had there been something like this, you would be comparing this with this, right? G with T. Hmm. So you are essentially comparing the word with the inverse of itself. And whosoever comes smaller, print that out. It's the same approach as Rumens. And yeah, now let me see other approaches as well. P. Malik, if you sort the DNA, then I think, as Manish is mentioning, I doubt that will work. I'll show you why. ACGT is the people with ACGT and AGCT are not, as per the problem statement, they should not come together. They should not come together, right? But in case I sort the DNA, if I sort the sort the characters of a DNA, then it is going to be a problem. All right, all right. So we have got, okay. Assign values to each values and add the if the values. Wait, Sanjay, I missed your answer. Let me just read it out again. Assign values to each values and add the if the value is same, then user is same. Okay, Okay. Okay. So Manish is saying that duplicate the key pair once with the way it is and the next with the way it is inverted. Good point. Good point. So what he's saying that if we have got AGCT, generate generate two keys out of it, AGCT, and we have TGCA, that is one key, and the other key that is possible out of this is is probably this. Is this what you're saying, Manish? Is this what you're saying? Oh, what you're saying is okay. Okay, I got it. I got it. So what you're saying is one with this way, other with this way, right? Yeah, user one and user one. Right. Good. So yeah, that approach will also do. It's just that in output you will have to deduplicate again. Okay. In the output you will have to deduplicate, and that is going to be a little difficult exercise. All right. Great. Great. So we all are on the same page, probably. Correct me if I'm wrong. So we need to bring user 1, user 2, and user 4 as suggested by others, I mean by all of you, is let's take let's take a DNA, invert it, compare it with the inverted one, and see who is the which one is smaller, which one comes first, and give it out as key. Okay, so let's take this example. Let's take this example. So we have got ACGT and user 1. So we have to inverse the DNA, mirror the DNA, and then see which one is smaller, the mirrored one or the actual one, and make that as a key. And why are we doing that? So that for mirror or identical, we get the same key. Okay? When we compare two values, if we are doing minimum, whether we are saying minimum of 10 and 5 is always 5, whether we say it minimum of 5 or 10 or minimum of 10 and 5. Similarly, minimum of ACGT and minimum and TGCA is going to be the same, irrespective of whether the mirror one comes first or the actual value comes first. So ACGT is what is going to be generated for user 1. And for user 2, we'll be comparing TGCA with ACGT. Again, user 2 will get the key as ACGT. Sounds correct? Alright. So the way we are generating key is we reverse it, TGCA, and compare with ACGT. Okay. Which one is smaller? Which one is smaller? We take that as a key. Here, after we reverse TGCA, we'll get ACGT, and out of ACGT and TGCA, we'll this is wrong. This is wrong. Okay. Yeah. So what we are saying is that we inverse it and then compare the way we are comparing this one and this one. So we compare first. If that is same, then we compare the second one. If that is also same, we compare the third one. Okay. If that is also same, then either one will be fine. Okay. So for the cases where we have a, the inverse is going to be again the same. So for a and a, the minimum can be will be a. Okay. The minimum will be a. All right. So basically, if first letter, last letter same, then we go to the next one and we compare and move on. Okay. Sounds good to everybody? And why are we doing all of this magic? So that as we talked about that whatever key we give to MapReduce framework, it brings all the values for that key together. And here we are trying to bring all those users whose DNA is identical, as well as those users whose DNA is the mirror of image of each other. Therefore, we are trying to form a key which is same for both kinds of users, which is identical for which is same for a user and and another user who is a mirror image of this one, right? Therefore, what we are trying to do is we are trying to compare the DNA and its mirror image. All right, sounds good to you? So we are trying to basically exploit. We are trying to exploit the MapReduce's quality of bringing keys together to solve our problem. All right. And you will soon realize that most of the work which SQL does can be converted into a MapReduce phases. Great. Now, so we had this another problem of voting. In this problem, we talked about a democracy where votes are counted based on the worth of people who voted for a person. Okay, so the richest gets the value of the richest person has got the highest vote, while the value of the value of the poorest person is has got the lowest value, and so on. So if a poor person is, lot of poor people are voting for A, while few rich people are voting for B, B wins. Okay. So we have to do this computation in that manner. Okay. Casey Reddy is saying that select. So how do you do such kind of problem? Let me just pick it and copy it and put it in editor. So this is okay. All right. You also try to give your answer. So as the SQL query is going to be okay. So join. All right. I'm just trying to reformat the code. That's all. Okay. So what he has done is join votee and person's worth, perfect, and join voter and this person and sum the worth. Good, good, good. Right. So as you can see that it's quite straightforward when you use SQL. But how would you do? Okay. Now here we are trying to say the key is voter, this votee, okay, and the value is worth. Okay, so you are basically doing the MongoDB way. Good, good. Okay, so what he's trying to say is the for the first one, my key is going to be voti. Okay, value is going to be okay, and then emit at the key value. Okay, let's say that is correct, and then in reduce. Mhm. That's going to be a little more tricky. Okay, anybody else? Anybody else? So I'm just trying to go through on one solution given by you. So this one is what is bothering me. This is what is bothering me a bit more. Okay, because for each time you are going to make a lookup, that is something which is hurting. All right, think about it a little more, and you should be able to. Okay, so the problem is that you have got two lists. One list is voter and votee. Who voted for who? A voted for C, B voted for C voted for F, voted for B. Okay, and list 2 contains their bank account details. The person A has got 5 rupees or 5 lakh rupees in their bank account. B has got some 1. C has got 11 and so on. Okay, so when you sum it up, A and B, so A and B 5 and 1, so C's worth is going to be 6, 5 plus 1, while the value of F is going to be 11 because C has got a worth of 11. C and C voted for F. Okay, the vote count of B is going to be equal to that of A, which is 5, right? And nobody voted for A, so A's vote count is 0. All right. So can somebody else put little more light on this? I'm waiting for your answers. Okay. So let me just Okay. All right. So yeah, Casey Reddy, that's what is the objective of this exercise is that we are trying to figure out how do you make it possible to join two tables using MapReduce. Okay. Okay. Map emits votee and voter. Say A colon B comma C. Perfect. Perfect. And then basically do the same thing as in select query. Can't we store list 2 in a map? Interesting. Interesting. So the problem with this approach, Ajit, is list 2, if we store it a map, then you would require the memory of the size of this list. In case this list is small, really huge, say it has got a few hundred GBs, okay, say 300 GB in this list, because there are people some millions. Therefore, we can't really store it in a memory. If map means hash map you're talking about, or any other dictionary you're talking about, right? Okay, okay. Just think about it. Let's take a break for 5 minutes. Okay, break for 10 minutes. Think about the problem, and then we come back. Okay. Also, I'm leaving the answer of this question. So go through it, and then we in the break time, and then we discuss after we meet. Okay. Hi, I'm back now. Hello. Okay, so is this solution clear to you guys? And you can compare it with yours. So this essentially involves two phases of MapReduce. In the first phase, all we did was combine together these values. And the key is the voter from the first list and and the person from the second list. Okay. So when we combine together two files, we get this, and then essentially, as part of the I mean here, as part of the reduce phase, all we got is the you can say that it is reduce. Okay. As part of the reduce phase, we got this phase 5 comma b comma c. For each person, each voter, we have got one value as wealth, and the rest is their okay devotees names. Sounds good to you? Now here we pick up one value. All right, the values are not sorted. They come as we are joining two files. So if list 2 is before list 1, when we are concatenating these two, then this value will come before the other values for a, and after the reducing. Okay. Now here this is very important part. This is very important part. So in first phase of reduce, so first phase of reduce gives you this much. Is this clear to you? All it did was it combined the the value of one particular voter and all the people who he voted for. Okay. So A voted for B and C, and A's value is 5. It's a single array containing two kind of a data types. All right. In the next phase, what we did is interesting. We pick up the first value. We pick up the first value, and and we for each of the rest of the values we print it out. Okay. Now, what does it mean? We are saying that because of this transaction where A voted for B and C, because of this, B got a value of 5, C got a value of 5. Okay, while A got nothing out of this one. And what does this represent? A voted for B and C, and A's wealth is 5. Now all we did was, because of this, we printed out B's wealth got 5, C got a wealth of 5, A got nothing. Okay, so the key is the people who got voted. Okay. Here only B and C got voted while A did not get voted, so A got 0. Here we are putting this particular dummy element A0 just to ensure that in output we have A0. Okay. You can, for time being, you can ignore this value, these two values. Okay. All right. So because A voted for B and C, B got 5, C got 5, the value of A, and then B voted for C, okay, because of which C will get a value of 1, and C voted for F and C's value is 11, therefore F will get a value of 11. Now, so this is your second mapper. Second mapper took the input from the first phase and converted this value. Now if you just simply sum them up, you get the result. It's as simple as that. Okay, is this clear to all? No. Yes, the first phase involves basically merging two files. A- and and even if there were 10 files, we could have merged it in a similar fashion. Okay, the only thing we need to ensure is their key is correct. In these two cases the key is same. All we are here because the we are merging on the basis of first one and here first one, and therefore it's straightforward. Okay, had this file been that worth comes before person, then we'll have to first run a phase on the second one such that worth becomes first one and well person becomes second one. Even if there had been like more lists here, we would be merging it in the similar fashion. Okay, okay. So we had got two lists, list 1 and list 2. List 1 contains who voted for who, list 2 contains who got how much worth. Here we already have, imagine that we already have got these in the form of tab separated values. Okay. Now as part of mapper, we will basically concatenate these two files concatenate these two files, because mapper can take values input values from multiple files. All right, and then generate the key as the in first case the voter will be key, and the second case the same thing, the first value that comes in will be the key. All right, now this is what we get as key value. Okay, for a the key is a and the value is 5. Similarly, A, the value is C as well as B. Okay, and they get combined together and you get this output. All right. Basically, we are trying to merge all the values of A. And the values of A in these cases is first the worth of A, second the people who got voted by A or people who A voted. All of these values together we combined and we get this kind of a listing. Now, in the next phase of mapper, the second phase of mapper, what we did was we picked up the first value and multiplied, basically gave out B and C. Okay, so basically we gave 5 to B, C to B, because A voted to B and C and A's value is 5. So we gave B and C the 5 value. Similar is the case with 1 being given to C, 1 being given to C, and 11 being given to F, 11 being given to F, and 12 is being given to nobody. And then we sum it up. For A, the value is overall value is 0, B, the overall value is 5, C, the overall value is 6, and F, it's 11. Is it clear to you? This one? Yeah, you can, I mean, it's actually not reduce really. Okay, you can say it Hadoop. And it doesn't really have much of a mapper 2 is the second phase of mapper, second mapper. Okay, It's basically second mapper. I think I confused you all, or is it clear to you? All right, great. To another example, a little bit more complex example, I have done a matrix multiplication. Okay, so you should look at www.knowbigdata/blog, and there you can have a look at the multiplying a matrix. So I've written a MapReduce job to do a multiplication of matrix. Okay, okay. You can have a look at the map. That is a little more bigger, complex example, and specifically when you are multiplying really huge matrix. If you are multiplying, say, a million column by million rows, a million column by million columns, or million columns into million columns against a million columns against million columns, then you are definitely, you cannot run the matrix multiplication using a single compute engine or single computer. You'll have to have a distributed algorithm for matrix multiplication. Okay, and this one would suffice. The one which we have done here would be sufficient. Okay, so any questions on this particular voting example? So although you will not be doing most of the work this way, most of the time you will be using SQL or Pig Latin or similar solutions for doing this kind of problems, for doing the voting kind of problems. Because as somebody from the class did it really nicely, okay, quickly using SQL. The SQL actually makes more sense to do joins and to do this kind of operations. Okay, and fortunately, Hive as well as Pig both provide that kind of facility to join these kind of tables, and this is pretty straightforward. Now, why am I wasting the time on explaining these problems? Why am I taking you through all kinds of MapReduce problems? Because that will give you a thought clarity on how to think in terms of MapReduce. Because all of the other tools such as Hive, such as Pig Latin, such as HBase, and such as even the new Apache Spark, they all behave, they all have the provision of MapReduce. Under the hood, they have MapReduce implemented. So it is very important to start thinking in terms of MapReduces when you are dealing with problems with large scale. Okay, when you're dealing with problem with the large scale, then these make a lot of sense. These make a lot of sense. All right, now the next is, now MapReduce should not be used in all kind of problems. There are few limitations and we need to be cautious about it. We need to be cautious about it. So if your work, if you know for sure that your work can be done using a single machine, there is no point in going for MapReduce. Okay, no point in going for MapReduce. Okay, so Manish's question is, are there scenarios where you have to use MapReduce instead of Hive or Pig? Yes, there will be scenarios. There will be scenarios, and you will have to use MapReduce sometimes, once in a while. That will be very rare. Okay. For example, the example I have given of the matrix multiplication. cannot be done so easily using pig Latin. Okay. And also, yes, unstructured data processing, you will invariably have to use it because, say, video processing or any other thing, which can be done using a programming language like Java or C, C++, better than your any structured query language. All right. Just like saying that why do we need J2E application when everything can be done using SQL. Okay. So there are a lot of things that should be done with the normal Java programming or any other programming language. All right. So there are few things which should not be done using MapReduce. Okay. First, when single machine suffice, don't bother about using multiple machines or doing distributed programming unless you see in the future that you're going to move to your data is going to increase and that cannot be executed on a single machine. Only in those circumstances you should be using multiple machines. And second is the computation depends on previously computed value. For example, Fibonacci series. Okay. In cases of Fibonacci series, you should be basically doing computation. I mean, you should not be using in case of Fibonacci series or any other thing where your work depends on previously computed values. Okay. When I say previously computed value, you are expecting the output of one mapper. Say there are 10 mappers being executed parallelly. You want the output of the value of in the first mapper to be used in the second mapper, or maybe in the second same machine on this in a different map phase. Okay. In those cases, there's no point in using MapReduce. Okay. You'll have to do a lot of thinking through how can you convert a problem into MapReduce in the cases where your computation requires previously computed values. Similarly, since most of the MapReduce things are batch process and should be done should be running in the background without too much of time expectation from you. Okay. You should be avoiding searching and ad hoc indexing, quick searching using MapReduce task. Okay, MapReduce task is great for resilience programming, great for doing computation in the batch. Okay, in a scheduled time manner, but it's not great for doing it live. It's not great for doing it live. Third one is if your algorithm depends on a global state. If you need to maintain that concurrency, that don't run any other MapReduce when I am doing something. Okay. Say using MapReduce, what you have done is you are trying to use some kind of a global variable across all the MapReduce tasks so that you can have a you can have a control over other MapReduce tasks also. Okay. Or you are trying to have a static variable. In all these circumstances, the MapReduce will not work. So those who are aware of static variable, global variables, or some sort of that, or maybe a central cache, MapReduce would not be a very useful thing in those scenarios. Okay. Because central cache will impact the performance of each mappers. Okay. Now let's talk about testing. All right. So this was what we talked about just today is MapReduce and four problems which we had discussed earlier on how to convert them into MapReduce. Okay. Now how do you test? How do you test MapReduce? So first, test on very small data. Okay. First, test on very small data. Do not just start testing on big data. First, try testing it on few small text and then fix those problems related to that. Second, test your mapper and reducer parallelly and independently. Okay, so you know that what to expect out of mapper and you know that what to expect out of reducer. So test them independently and individually to fix the problems related to both of them. Okay. Also, since in future your mapper and reducer code are going to be independently changed by various developers, you should have built your test cases for individual map reducers separately so that in case people are modifying it in future, you can start using it. Okay, you can use the same test cases and both can be okay. So I mean that's a part of unit test casing where each mapper and reducer is generally a separate unit. Streaming jobs can be very simple manner. They can be tested using a simple command. So you do a cat input file, then run mapper, then sort, then give it to reducer, and you'll get the output. Okay. So this is a very quick way to test your streaming job in a very simple manner. While when we do a testing for Java or other programming languages, you can use MRUnit. MRUnit is the JUnit version, Java JUnit version for MapReduce. Okay, basically it contains few more libraries which gets added to your JUnit, and we'll talk about it. Also, if your program is basically testing a huge text. Okay, if your program is testing a huge text, you would like to basically if you are testing a huge text, you would sorry, I'm sorry, I'm getting a lot of noise, so I'm getting disturbed. So give me a second. Hello. Okay. Okay. So yeah. So when you are testing predictions, okay, when you are testing predictions such as recommendations or any other way, the best way to do the predictions is divide your data into half. Okay, divide your data into half, and then first, based on first part, you generate your predictions and compare the predictions against the real values of the second half. Okay, imagine that you are basically validating that you are building a recommendation engine on movies, where you give the recommendation of movies to various users. Okay, you give the recommendation of various users to that you might like to watch these movies. So you first figure out the first half of data based on time. So sort the data, slice it into two equal parts, generate your recommendation on the first half, and then compare the values against the second half. So that is how you generally test your predictions. Okay. So I will talk about predictions later on also when we actually generate the predictions. And for those who are little impatient, here is how you write your Java code. Okay, here is how you write your write MapReduce is in Java. So you basically write a class called stub mapper that extends mapper, and you define the kind of input, the data type of the input key, input value, and the data type of the output key and output value. Okay, so I'll show you the actual one also so you can see. So in this example we are doing a word count. Okay, or you can see this one. All right, so here we are talking about the mapper, where how do you write in Java. Okay, so this is your code, this is where you write, the rest is how you define it. So first you create a class called stub mapper that extends mapper that extends mapper. Yeah, this is all 2.0. Okay, all right. So and the value, so basically you implement a function called map in a class which extends mapper, and here you define what what is your data type of the key values. So those who are not from Java background, they might find it little awkward, so but those who are from C++ background, they'll be able to quickly correlate it with templates or generics, they used to call in C++. Basically here you define that my stub mapper is of type mapper with these data types. Okay, where my key is of type object, value is of type text, and I will be giving out a key which is of type text and long. Okay, so in Java the data type of the value, instead of being standard integer or long, they have implemented a new set of primitives. Okay, so the input to you is given in value, right? So value dot to is string, and this key by default, if you are running a standard input mapper, running a mapper, the key is the byte count of this particular line, and this is the line by line you will get the input. So you take this line, get the string out of it. Okay, because text is not standard string, it is the data type that represent the strings in MapReduce. Okay, and afterwards you split it using space and tab. Okay, afterwards you split it using space and tabs, right? And after that you iterate over the array and remove the anything which is non alphanumeric and convert it into lowercase, and then put it out onto the standard output. Okay, here context represents, this is the place where you're going to output your key value pairs. So you are telling to the context that this is my key. Okay, you're telling to the context that this is your key and this is your value, and the value here is just simply 1. Okay, just simply 1, that's all. So that is just mapper. When will we use key argument? You mean to say this one, the first argument of the mapper? Yeah. So this is the byte count. Sometimes you have to know on which byte you are while you're dealing with the file. Only in those cases you will be using that. Okay. In normal circumstances, you may not. Okay. And byte count makes sense. It is not line count, it's a byte count, because line count would mean, because this file is going to be sliced into portions onto HDFS. Therefore, counting line will be difficult, will be very difficult. Right? Therefore, MapReduce gives you the byte count. Okay, so you'll be using it when you bump into some use case where you need to figure out on which character in this file are you on. Then you might require, or when you need to know that this much of text has already been processed. All right. Yes, the output of the mapper has to be key value all the time. Yes. Okay, value can be object and value can be anything which is serializable. All right, now that is mapper. Now, the reducer for this process looks like this. Basically, you create a class called stub reducer, extend a reducer. Again, you define the data type of key value. This data type key value will be same as the output data type of mapper. Okay, the input data type for a reducer will be same as the output data type of a mapper. Text int writable. In my case, I've just changed that to long writable. I'm expecting the longer values, bigger values. And as a thumb rule, use long writable over int writable if you are expecting huge values. And the output is going to be double this time, double writable, and the input is text. Right? And once you are done with it, you glue them together. Okay, you glue them together saying, this is my stub driver. Okay, this is my stub driver. Okay, and this step driver is going to be your entry point. So as you can see here, the way I have done is that I've created something called job conf, then job, then you have added. Okay, and here you can define how many reduced tasks you want. Okay, how many reduced tasks you want. Okay, also you can define how many mapper attempts you want, how many reducer attempt you want. Okay, and also you can cache some files. So job conf is sort of a configuration of the job which you're going to execute. Job conf contains everything related to the job. Okay, and based on the job conf we execute the work. And I'll say that job conf is very, just a configuration parameter. Right? Most importantly, the job itself has lot of arguments which you can use to your benefit. Okay, there is something called partitioner. We'll talk about partitioner. There's something called combiner, combiner class. We'll talk about all of these. So this is how you generally write your Java program. Right. So Manishi's question is that this implementation would be same for both V1 and V2. So when we moved from V1 to V2, the program for V1 used to run for V2, okay, but not the other way. If you have written your code in V2, you cannot run that on the older version. But this one, yeah, but therefore this one is on V2 and therefore it won't work on V1. Okay. So when we were moving from V1 to V2, initially there was not much change in the libraries, but in later versions there were new functions added and new descriptions added. And slowly, those things part of the V1 have been deprecated. So we'll stick to this standard only. Okay, we'll not bother about the other one because this is something the current one. This is what is acceptable. All right. Now, the example has been uploaded onto the sessions. You can have a look at it also, and we'll talk about in more details about both of this. Where is the output of mapper is set as input for reducer in this example. Okay, so that is something being taken care by Hadoop. Okay, we do not have to set it because it is imperative. Okay, all you need to do as part of this one, all you need to do is define these two things. You define your mapper, you define your reducer. Both mapper spits out the key value pairs. These are the end result of the mapper. And reducer takes care of all the values. A- Reducer is basically given all the values for a particular key, and reducer had to do some sort of accumulation. Here, reducer is iterating over the values, summing them up, and then returning the value. Returning as in writing it into the context. That's all. Okay. So there is mapper, there is reducer. You don't have to tie them directly. They have to tie them using a driver. You are saying to driver that this is my mapper, this is my reducer. Now Hadoop will itself internally take the run stub mapper, give the output of the stub mapper to itself, sort it out, so order that output of the stub mapper, give it to stub reducer after sorting and grouping. Okay, so we don't. This is the only gluing we are doing. We are saying this is my job, and this is the mapper class. This is the reducer class, and this is the file I am trying to. This is the file I am trying to read. Okay, as input, and this is the file I am trying to output. That's all. All right. Okay. So Ajit's question is that is it done in practice that mapper reducer calls external system DB or web service? It does. It does. Okay. So, but mostly we try to avoid it as much as possible by first moving data to HDFS or to HBase. But when we are moving the data from an external system to HBase or Hive, what we do is we basically do the MapReduce processes parallelly, and all these processes parallelly hit the database from multiple mappers and move the data from databases onto Hive or HDFS. Okay, but we should avoid that as much as possible because first, our mapper reducers are going to hit it very badly. both service as well as databases, because there are, if you are running hundreds of map reducers, it is going to hit the servers really bad. All right. Now, as an assignment for the next class, code all these MR problems in your favorite language, whatever it is. Okay. Now, the next assignment I want to give to you is, you are given a huge text. Imagine you are given a huge corpus of text, and what you want to do is, you want to find a recommendation of the next 5 words. Okay, because you must have been using, say, Android or some other phone these days, smartphone, where you type a word and you see these recommendations. Say you type happy and you see the recommendation like birthday, new year, marriage, as well as if you type how, it shows you recommendation like are, do, did, and so on. How does it do that? So on the application level, it will be asking the server, or it will be having a dictionary, that after happy these are the top 5 words you can show. So it will have a huge dictionary for each word, what are the top 5 words to be displayed. Now, our objective is to generate this kind of dictionary which has the next 5 recommendations, or next recommendation of top 5 words. All right, that is our objective. And what is our data input? Our data input is, say, a huge corpus of text from Wikipedia. You are given a huge corpus of text from Wikipedia. Based on that, you need to form this sort of a dictionary, that for a word, what are the next recommendation to be shown. Okay, that is your assignment. Please list down your approach in this assignment. Okay, list down your approach for this assignment. Okay, now I'll just take a few more steps and try to do. So I will actually, before we separate, I'll just try to run this. Okay, I'll just try to run. Okay, so do you have questions for me at this point of time? Okay, so let me just take this file and do export. So this is the project of Java where you can, hold on a second, where did it, so whenever you are done with your writing program, you generally export it, and here this is the word count, so it will be copied to this place. Now I have to take this jar file to the server. On Windows machine, you will have to use something called WinSCP, and here download word count.jar, and I'm saying student at hadoopfun.nobigdata.com and ASCII folder. So it's copied, and to run it, all I have to do is, so I say Hadoop jar ASCII word count and the file name which I want to process is input. Okay, that is the folder I want to process, and I want to save the output into jar. So we need to put the class name which we want to mention as the input points. Here our input driver is this one, right? This is our input driver. So I say sg dot our stub driver. The okay. So basically I'm saying Hadoop jar, and then and then okay, Hadoop jar, and then the jar file, then the entry point. In this case our entry point is stub driver, and then it is doing the work. Okay, so this is the exact command I'm using. This is the exact command I'm using. All right, now I've got few questions. Yes, the Java package will be available, and it's I think already available in the Hadoop on your LMS. Okay. How to view your jobs, see if they have completed or failed. You can see the jobs as soon as you start any of the Hadoop command, it gives you a URL to track. First is that. Okay. Second is you can go to the okay. So here this is showing you okay. This is some, so whenever any process starts, the Hadoop gives you a URL which tracks the progress. So it has already finished, but still it should work. So it has finished, and the output would be in what folder? In the asgiri output j. Asgiri. Yeah. So Manish, as you can see that here you see the history of this job. There were one map and two reduces. Okay. Why were these two reduces? Because we had mentioned in our code that we want two reduces. You can see number of reduces task, and this was running on which machine? Though we started at Hadoop 1, but the process, the tracker was given to Hadoop 2. Okay, and the first task is being executed where? Hadoop 4. You can see Hadoop 4, and and second task was being executed at Hadoop 2. Okay, all right. As you can see, that was reduces. Let's see about our map. The map task was being executed on Hadoop 2. Okay, and the reduce task, as you can see, there are two reduce tasks, one here and other here. Okay, okay. So this is my command. All right. Hello, hello. Great. So, yeah. So try to attempt this problem which we had discussed today, specifically this problem. You can download the content of the Wikipedia using this URL. It gives you the details of the content of the Wikipedia, and you can go through it. And also the on the learning management system, it should be available to you. It should be available to you over here. In the session number 4, the sample project is available to you. Okay. All right. All right. All right. So, do you have any other questions to me? Because today it is pretty much for today, and we'll discuss rest of the things in the next session. Try to attempt all the problems which we have discussed today in any of your favorite programming language, and try to do that. Okay. We'll be sending you a separate quiz also. Okay. We'll be sending you a separate quiz also by end of Monday evening. Okay. By end of Monday evening, you'll get a separate quiz also which you need to solve based on these last two discussions. Okay. Yeah. Thank you. This is pretty much for today. Have a good day. Okay then. I'll hang up now. We'll see you tomorrow. See you on the next weekend. Thank you, Pimali. Bye bye. Have a good day.